Welcome to the Digital Amateur Television Experimenters Night. This is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. You realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world. Also participate in the night by coming up to the Queen's Domain clubrooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30pm local time. We'll see you soon. This is VK7 OTC.
Okay, this is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night. And I have Rex, VK7MO. Hello, Rex.
Hi, Justin.
And Andrew Klekocuik in the studio. Welcome, Andrew.
Hi, Justin. Thanks.
Now, we're talking about some fantastic auroral propagation that these two and
Brody
two
and Jeff.
And two in Victoria.
Yeah. 3 MAP and 3 KRG.
KRG. Jeff.
No, KGR.
KGR. Okay. So, just before we get underway with that exciting news, just wish to acknowledge Tasmanian Aboriginal people as the traditional owners of this land and pay my respects to elders past, present and emerging, for they hold the memories, the knowledge, the culture and hopes of Tasmanian Aboriginals. So, what has been happening?
Okay, let's go to...
now you're testing me.
Right.
Now, if we go to here, I love it. Okay. And we go to here and press this button and hold my tongue in the right place.
Yes. Well, let's. This update relates to a couple of events that's happened since our last.
Nearly there.
Our last report, and also to an event which we expected, which was an absolute fizzer. So,
okay.
So now on the 1st of December there was some pretty spectacular stuff. If you look on the web, I've picked out a pretty spectacular picture.
Definitely.
And they said, this was the ABC website, and they said that it was seen as far as western New South Wales. This particular photo is of the aurora only about 20 kilometres south of Perth.
Wow.
So, next slide. Now, the events that we've seen since our last report on 5th of November we had a pretty good event on the 22nd of November, and you can see there 2 meters, 256 decodes, 6 meters, 266 that 3MAP got. KGR,
Wow.
who is about 80 kilometres further north than MAP,
Okay.
so you need a better aurora, a more northerly one for him.
Okay.
He's also about 200 kilometres further east, so you wouldn't expect necessarily similar results, but a lot of it is very similar once you can actually see it.
Okay.
And then on the 1st of December, you can see 549 decodes, 786 on 6 metres, some of which is a mystery, in as much as they occurred at a time, or some of them occurred at a time when 2 metres was not present.
Happening. Okay.
We really don't know what sort of propagation, but Andrew's got some thoughts, which when we get to it, he'll let us know.
Great.
And as well, then, we were expecting big things on the 4th of December, and we'll discuss that later, which turned out to be nothing. Next slide. Now, this is the 22nd of November, and the interesting thing about this is the 2 metres, which is in blue, is sort of averaging around 350 hertz of Doppler, and 6 metres is probably only averaging about 35 hertz, so 10 times less. Now, you can explain a factor of 3 to 1 in terms of wavelength, but there is something else involved, so that we
Some
don't
other mechanism.
well,
here.
I don't know that it can be another mechanism, but it may be to do with the fact that our beam widths are much wider on 6 metres, and when the aurora goes overhead, you get a different result than 2 metres, which is sort of still beaming at the horizon and seeing the aurora still further away but we don't really know. Well, I don't know.
No, that's right. I think you're right, and it's probably something to do with a different part of the aurora that we're looking at, different height, or different features.
Yeah. Now, we have in the past had a reasonable correlation between 6 and 2 metres by that factor of wavelength difference.
Okay.
So it doesn't always happen this way.
Okay.
Now, there are, on this plot, probably hard to see, there's some little green triangles here, and that's KGR further north, and he only saw it for a short period, which demonstrates that just that 80 kilometres further north makes quite a difference. Okay, next slide. Now, this is Andrew's diagram, so I'll let him talk about it.
Yeah, so this is the analysis of the NOAA ovation auroral forecast. So this is actually a forecast of where the auroral oval would be based on satellite data. So this is taking in solar wind data upstream at the L1 point, about 45 minutes ahead of the Earth. So it's a forecast based on real data, and I take the JSON files and find the nearest edge of the auroral oval to Tasmania, and that edge actually is an estimate of the where you'd see aurora at about 120 kilometres altitude, and then I work out the distance from Rex and from Brody, and Rex is shown there in blue and Brody's in the orange. So that's at the bottom of the plot there, so that's universal time running across the bottom axis, and up the vertical axis the elevation of the aurora is seen from those two locations. So you can see that on that particular day, 22nd of November, the aurora popped up after about 6 UT for Rex, and because Rex is further south, it's higher in the sky. It's up to about 40 degrees altitude.
Yep.
The red line above that's the magnetometer from Hobart, so that's the Bureau of Meteorology's magnetometer at the Lee.
Okay.
That's the horizontal component, which seems to relate pretty well to, at least when it's disturbed, when there's an aurora in
So
the
what you
vicinity.
see, what you would actually...
Yeah. So it's kind of a measure of the disturbance in the magnetic field from the ionospheric currents
Okay.
in this horizontal component. So it popped up for Rex, and a little bit there for Brody, and then it retreated over the period and kept going even past magnetic midnight. Now, on that there, I've got some lines, vertical lines, sort of a yellow and a kind of a reddish line there, and that's when Brody was seeing his main decodes, and it sort of corresponds to when the aurora is above his horizon.
Okay.
Later on, he didn't see anything, and the aurora is pretty low as seen from his location anyway. So,
Is there any correlation? Because the magnetometer reading, like there is a transition here, it goes up, and there seems to be more decodes, and then it goes down here, and that was when Brody was... no, that's the yellow. What's the red?
Yep, that's when Brody's
Yeah.
finished. Yep.
I just... Anyway.
Yeah, it is related. It's essentially like there's an impulse in the solar wind that causes the auroral over to expand. So that's the beginning part, and then basically the auroral currents keep on going for a while, and they quieten down. They generally come and go in what are called substorms. So there are just discrete periods of a few hours when the energy is pumped up into the magnetosphere and is released and dies away, and then gets re-energized again.
Okay.
And that's probably related to that. So, yeah, generally this this analysis seems to match reasonably well. I've calibrated the advance and retreat of the auroral oval based on satellite imagery from the VIIRS instrument on one of the NOAA polar orbiting satellites that can see the aurora at night, and it's quite a good match between what they see and what the auroral oval forecast.
And that's visible
And infrared, yep, that's right. So that's a low light detector that sees the aurora.
Okay.
And that's not a forecast, that's
No,
real.
that's a real image.
So
Okay.
it's a little bit different
Real
to
time. Yep.
the NOAA 45 minutes.
Yes, that's right.
Yeah.
But it's still based on real data.
Yeah.
So where's that satellite received from? Antarctica somewhere?
No, well, I guess there are a number of ground stations, but none in Antarctica that I'm aware of, but they do have store and forward on that satellite as well, so it's not necessarily all real time.
That's an orbiting satellite. That's not a...
That's right. It's what's
geostationary.
called the Suomi NPP,
Okay.
National Polar Partnerships Satellite,
Okay.
and I think it's kind of it might be NOAA 20 in the catalog. but
Okay.
there are a number of those that have some ground stations in Alaska and Hawaii and other places.
Okay. Great. Cool.
Okay, next slide. Now, then we move on to the 1st of December, and a bit hard to see, but there are green areas which and blue areas, and a lot of them are very close and tend to overlap. The green is from Jeff KGR, and the blue is from Brody MAP. Then on the 6 meters we've got red from MAP and
Grey.
grey.
Ooh, there's not very many of them.
No, sorry, actually it's really these purple.
Oh, purple. No, it's purple.
Yes.
You can sort of see it. Actually, you can probably see it better on the stream.
Yes. On 6 meters. Now, again, we've got very little Doppler on 6 meters compared to up to 600 hertz. Doppler on 2 meters.
Okay.
And I guess the surprising thing is the Doppler shifted from positive to negative about 11.5 UTC. So before magnetic
peak here.
midnight, which is a little bit of a surprise. The other surprise of this is 2 meters dropped off completely between about 1500 and 1700, whereas 6 meters continued. And Andrew has a thought about why that could have happened.
Yes. So yeah, the aurora is quite active on that night, and in fact, it really heated up in the earlier part there, where it's advanced to positive Doppler. That's right. And then it died away for a period, and then there was another injection of about 1330 or thereabouts, or 1300. And then after that, there was a period of pulsating aurora, and we were kind of in this phase where there's an auroral drizzle of lower energy particles coming in, and I think that's something that relates to this drop off in the Doppler between the two frequencies. So just tending to see one frequency due to the lower energy particles coming in, and there are a few photographs around showing it's just a generally faint red glow around there, not very active at all.
Okay.
So, and does 6 meters need less ionisation?
I think it does, yes. I think it definitely does. So that's the reason. And then later on, there was a bit more of an injection of energy, and we saw the
See a bit of 2 meter come back and.
Yes. All right. Next slide. Now this is what the NOAA short-term forecast was showing. It's a little bit hard to see, but where is Tasmania? Can you see?
Well, it'll be just here. So.
Oh yes, there's Tasmania. So at 10 o'clock, the auroral oval is well south of Tasmania.
Yep.
Nothing was copied.
Yep.
Then the auroral oval had expanded so that it was
enveloping Tasmania.
all of Tasmania into southern Victoria, and by that time we had some signals, and it actually increased very rapidly, so that some of this Doppler peak is a function of the movement, the physical movement of the aurora towards us.
Okay.
Then later on, it's gone negative, but it hasn't actually moved away, so I'm not sure.
So this is magnetic midnight in here?
No, magnetic light's at 1332.
Oh, okay.
So, doesn't quite...
No, as we'll see shortly, there are some other reasons potentially.
Yeah. And then towards the end, the 6 meters is still there, but
there's
essentially nothing.
Yeah, the oval's moved right around.
So this residual stuff that Andrew was talking about must have still been present.
Okay.
Okay, next slide. Now, this is Andrew's diagram at the bottom, and his Keogram there showing the aurora, the pinky and is that green aurora? And I've written lines up and down. The A line fairly reasonably equates to the sharp increase in the aurora. In the movement towards us.
Yep.
The B line shows it going away, but it really doesn't go away, at least on Andrew's diagram. The C line does show a drop in the aurora, but doesn't really go negative until the D. So
Okay.
doesn't quite add up, but I think it's a fair chance that there's probably short-term things going on that we see on radio that.
That's right, yeah. So that auroral oval analysis is quite broad brush, and it's not showing individual features in there, and there'll be ribbons and marks and all sorts of other features that we might be seeing individually as things happen. But just noting, in this case here, the underlying bottom diagram, that's the version of my auroral oval analysis for the 1st of December, which in this case shows the aurora much higher. In fact, it's overhead here, well, nearly 80 degrees. The resolution of the underlying data, the ovation data, is 1 degree, so I only really get around about 1 degree of latitude resolution in where the aurora is, and that corresponds to a fairly, sort of coarse resolution once you transform it into an elevation above the horizon. So it's kind of not like 90 degrees or even beyond 90 degrees there, but for Brodie it was actually probably up to about 50 degrees, and that kind of tallies with what folks were seeing in Victoria and even further north into New South Wales and parts of Western Australia. You can see that the red magnetometer trace is quite active. It's quite, zooming around in there, and that's quite interesting in its own right.
So is that showing those variations within it? Like, is that actually indicating that there are peaks and troughs?
Yes.
Yeah. Okay.
And that's related to the speed of the solar wind buffeting the Earth's magnetosphere and energising things.
So there's a fair bit going on.
Yep.
Like
it's quite active.
It's,
and that relates to that Keogram, that's from my all-sky camera, a cheap all-sky camera, Moonglow Technologies. They don't make them anymore, but it's taking a picture of the sky every minute, and the software is quite smart. It pulls out the column from north to south across the image, across the meridian, and then just stacks that in time.
So that is effectively 180 degrees that you're looking at the top's north and the bottom south?
That's correct.
Yeah.
Yeah.
Okay.
It's a 180 degree field of view there, and I've contrast stretched and colour stretched that a little bit to bring out the aurora. Earlier in the day, of course, it's just the daytime sky with clouds, and after about 20 UT, it's the morning sky. But it shows it up pretty well, even on that night where it was fairly cloudy, high to mid-level cloud in Tasmania, it comes through. But yes, those red streaks line up with some of the magnetometer variations there, and the aurora did go.
And it's north
beyond,
to south, like it's overhead and past.
That's right. Yeah.
Okay. Wow,
Now,
there's a lot going on here.
Yes. and the other thing is that in terms of the 2 metre data, it pretty well equates to this peak, and then another burst here, which only Brodie could see, which Jeff couldn't see because he's further north.
Which is good correlation. That's
yes. Yeah.
And there's a variation here.
Yes, the magnetometer did something to produce some activity. Okay. Now, this is Andrew's diagram, which I will hand over to explain.
Right. So there's a network of what are called SuperDARN radars, Super Dual Auroral Network radars, and SuperDARN was established in the Northern Hemisphere. Ray Roble is the chap that developed these in the 70s and 80s, and actually started off with DARN, which was a couple of radars in Canada and the Arctic anyway, and it became SuperDARN when they added more. And I guess they added some in the Southern Hemisphere. Luckily it didn't become SuperDARN. But anyway. So there are a number of radars in the Southern Hemisphere, one of which is at Buckland Park near Adelaide. There's actually one at Bruny Island near Hobart here, and one in New Zealand. Unfortunately, the New Zealand and the Bruny Island radars aren't running at the moment, and that's a sort of symptom of COVID. They haven't got them up and running after COVID yet, but the one at Buckland Park keeps going. and it's a radar at about 10 megahertz, which uses over the horizon techniques to measure plasma velocities out to several thousand kilometres. In fact, the field of view of this extends way down to Antarctica or even out across the southern Pacific Ocean for Buckland Park. It's looking in a particular direction, sort of, New Zealand through to south of Tasmania. That's running continuously, and it's got, I think it's something like 20 different viewing directions, sort of scanning across. Anyway, it's able to get plasma velocities by measuring the Doppler shift at 10 megahertz, so it's quite a different frequency. The data gets ingested into a model, which then plots up the plasma velocity field, and it kind of relies on having several radars in there to actually get a reasonable map. Now the data that's actually coming off the radars is the little vectors that appear in some of those plots there. So there are snapshots of the plasma velocity in those little vectors. They're vectors that are plotted with a dot at the origin and a tail that points in the direction of the plasma motion. Now, so the next part of that is the colours. Why are the colours there? Well, the currents in the ionosphere also relate to this plasma motion. So the magnetic field lines in the distant magnetosphere map down into the ionosphere, and as the plasma moves along those, they kind of drag currents in the ionosphere. Ends up being two cells that sit over the polar cap. It's called the two-cell convection pattern. But that's generally in quiet magnetic conditions, and when it gets disturbed with aurora, that two-cell pattern can break up into smaller cells. It's a bit like weather. You get to see lows and highs, essentially. And that's what some of those blue and red patterns are, and that's that plasma velocity, or electric potential in this case, that actually comes from a model, but that's informed by the solar wind parameters and also the model of the Earth's magnetic field. So some of it's model, some of it's real observations. But the upshot is that we can get some idea of what's happening with plasma motions based on real data. The plots are kind of, they're developed in magnetic local time, and what I've had to do is flip them right to left to get the geographic map in the right sense for our brains, and not an upper atmosphere physicist brain. And also the other confusing thing is that the lines of latitude are actually lines of magnetic latitude in those maps, and then there's an auroral oval outline essentially in there as well. A lot going on, but a few things that are happening there. So in the early part of the night there, the 1100 UT, there's kind of a blue blob that's out to the east of Tasmania, and a red blob out to our west. And I've rotated those images so that Tasmania's at the bottom. And basically, without going into showing you each individual plasma vector, the motion of the plasma seems to tally with the Doppler shift, in that we're getting positive Doppler, we've got plasma moving towards us, and negative Doppler, plasma moving away, 11:45. Now, generally the plasma wants to flow along lines of magnetic latitude at the edge of the auroral oval. It tends to want to go east or west, and the magnetic latitude lines are actually inclined to the geographic latitude lines in Tasmania. The magnetic north is about 15 degrees east of geographic north, and if you play around with some diagrams, as Rex and I have done, you find out that if things are flowing along lines of magnetic latitude, they can actually have a north or south component geographically, which will give us a positive or negative Doppler shift in the right circumstance. So this is another part of the complexity of trying to understand all of this.
Okay.
And the final thing I'll say is that the thing doesn't actually work all the time, at least the model doesn't work, and I've got some unreliable conditions in there where things are quite shrunk back and it looks quite simple and there aren't many vectors in there, because at 10 megahertz on this particular occasion there was a lot of absorption and the radars weren't actually able to see very far at all.
Yeah.
And I noticed that on my home recordings where even the AM band dropped out quite substantially on that night. I mean, the local radio was fine, but anything interstate was absorbed as well. So
that's telling us that it's doing something to the D layer.
D layer, that's right.
Okay.
And that might also be another part of some of the dropout, at least in the 2 metre as well. There's another thing I haven't really considered too deeply, but that might also be another factor, even absorption at those frequencies.
That's the TEP that they talk about? The no?
So that's, you're thinking of
transequatorial
propagation.
TEP.
No, it's the wrong term. It's the electron absorption measure.
Oh, the TEC.
TEC.
Total electron content. Yes.
Correct.
Yes. That's right. And in fact, you can also see even in the ionoson data from Hobart that even the ionoson drops out. So, it's getting a lot of absorption. So anyway, there are some limitations in this analysis, and we're working through this.
Okay.
This is all kind of really, as they say on the website, not to be published, these plots, because there's still more information to go into them.
Okay.
And so I think we'll be able to look at some more detailed things. But
So preprint.
but we're just really trying to use this as a tool to understand another aspect of the plasma motion, because in this case we're actually seeing finer scale features rather than the broad brush auroral oval.
Yep.
And in fact, it's quite likely that some of these small scale features relate to individual auroral cells, if you like, or ribbons or filaments or whatever.
Okay.
And we might be able to get some quantitative data. The thing that we still don't really have a good handle on is at what distance the backscatter is occurring from us. We're looking south, and we, without actually having perhaps using triangulation of individual pictures of the aurora, we still don't quite know what distance we're seeing it. We've got some idea from the auroral oval analysis, we've got some idea from these plasma maps, but it would be nice to know within a few hundred kilometres
where it's actually coming back at you.
That's right,
from.
and what elevation it's happening at.
Okay.
Do you think there's any advantage to people at Buckland Park in the sort of data we're collecting?
Yeah, well, in fact, the folks that run this radar, that's actually La Trobe Uni, are quite interested in seeing what we come up with. In fact, earlier on in the year, I contacted them. They had a few outages, and even alerted them to the fact that their radar wasn't running. But
Right. Okay.
but still quite. James Devlin at La Trobe Uni is quite interested in these things. So there's a lot to learn still. It would be nice to have the New Zealand and the Bruny Island radars running, and I've been trying to encourage them in that direction, but it does require.
So it's La Trobe Uni that is running the Bruny Island.
Bruny Island. So that's at the southern end of Bruny Island.
Okay.
And that's been there since the late 1990s, I think.
Okay.
Yeah, the Antarctic Division used to help out actually with some of the logistics of swapping discs over and all that sort of stuff down there.
Okay.
And even Warren Nicholas,
Yep,
he used to help us out.
Well, there you
collect
go.
data and things like that. So.
and Warren's got a shack on, Bruni. So yes. Anyway, actually, Warren's probably out there. Anyway, okay.
Next slide.
Now you can see
Sounds
the
a bit more
vectors
detail,
here.
yeah, that's right.
They're
Yeah.
a bit better.
What you really need to know, though, is the north-south component, because that's the thing that's of interest to us, at least the geographic north-south, because generally we're, pointing our antennas south, and there's that inclination between the geographic and magnetic coordinates.
Now, because we're only 14 degrees off, the component is going to be
It's a small
very small.
fraction.
So these actual speeds of circulation have got to be
Quite high, and in fact, I think the vector in there, they're 500 meters per second.
okay.
Somewhere in there's a little vector, and yes, there
here.
can be quite a component of a few hundred meters per second, which will equate at these frequencies. I think there was a factor of 2, wasn't there, Rex, at 2 meters? So,
Yeah, because it's going and coming.
And that's quite complex because you can see the vectors are.
So it actually comes back to meters per second.
It
at
does.
2 meters. Yeah.
That's right.
So if you've got 500 meters per second as a component, you can have 600 hertz of Doppler. Sort of.
Yeah.
And you can see those vectors, they relate to those two cells, and between those two cells, so that weather pattern comment is very similar.
That's right.
It's the wind in between the two cells that.
Yes, that's right. The two major cells, they actually, and the point is that it's kind of somewhat counterintuitive. Like generally, when we look at the atmosphere, things sort of move from west to east, and we have a circulation around the pole.
Yep.
In the upper atmosphere, we have these two cells, and between them generally is the midday magnetic meridian. So you can actually visualise magnetic time. We sort of talked about magnetic midnight. Well, in that two-cell convection pattern, the plasma tends to want to flow from the dawn side to the midnight side across the pole, and then it returns around the flanks to complete the circulation.
Okay.
And so it has a preferred direction before and after magnetic midnight. And because of the inclination of the field to the geographic, that also causes the plasma north-south component to flip from towards us in the
that's what you
evening
see.
and then away from us in the morning. So
Okay.
that fits quite well, and the sort of speeds that we're seeing also tend to fit with what we expect the plasma to be doing.
And the shifts. Yeah. Okay.
There are some other complications now. We're only looking at when there are auroral conditions. We've got no idea really what's happening when there's no aurora there, and that's when the auroral oval's well away from us, and that convection pattern is well south of us. But
So
when-
it's regrouping.
yeah,
That energy's regrouping.
that's right. But when there's no aurora, we don't really know what's happening,
Yep.
and generally we're outside the cell convection pattern where there's quite a different regime on the outside.
Okay.
But yeah, generally we're seeing things inside the auroral oval or at the edge of it anyway, so it seems to all sort of fit together more or less. Now this, this two-cell convection pattern's been known for some time, but there's still a lot to learn about it, and it's really only probably in the last 10 or 20 years or so that we've really got a lot of detail on things, and there are satellites zipping over the top of that and actually mapping the plasma motion at different heights. And so the next thing, well, we've done a little bit of this already, is actually have a look at some of the satellite data which gets cross sections at different heights, because one of the things that we're not quite sure about, this plasma motion is roughly for about 400 kilometres altitude.
Okay.
Generally, some of the auroral features we may be looking at 100 kilometres, 120, generally at the base where there's much more energetic stuff getting down.
Okay.
And there can be some vertical shears in the plasma motion, and so while it might be showing us a particular direction here at 400 kilometres, that might not map exactly down to where we're looking at things. So there's still a lot to get through here.
But I just point out on this second diagram, that's fast. If that's their dots are really close together and it's heading between those two cells. So
Yeah, it can be up to a couple of thousand meters per second.
yeah, okay,
You know,
wow.
super duper fast.
And that's all dynamic there. That's then. This is a snapshot. This is. This is.
Yeah, and the other side of that is that, you know, there are electrons moving, and there's ions as well, kind of entrained in there, and that tends to drag a neutral wind, or this motion actually causes a wind in the upper atmosphere.
Okay.
At about 100 kilometres, it can map into, and can actually disturb the upper parts of the atmosphere. Actually, an effect of the magnetic field on the neutral atmosphere, not down in the troposphere, but up in the upper parts, actually causing the winds up there, dragging winds along.
And they're charged winds, like they're
charged winds, and then they drag the neutral atmosphere along with it, and it influences things like the chemical composition of the upper atmosphere. So,
wow.
it's useful to know about this for looking at even the dynamics of our normal atmosphere.
Okay. Cool.
Yep.
Next. Yep.
Yeah, I just threw that in. That's the lines of magnetic latitude, equal magnetic latitude there. You can kind of see that you know, there's a slope or a difference across Tasmania there. You can kind of see the interesting feature around South America too, where the South American anomaly changes the magnetic field lines as well. But yeah, just reminding folks that the magnetic field is offset relative to geographic coordinate system. And
Plates, yes.
yeah, we have a south magnetic pole kind of near Casey Station down south of Tasmania, and then there's the north magnetic pole, which is up in the Canadian Arctic. Up there somewhere, yep.
Oh, there you go. Okay.
And the magnetic equator, which is, I guess, something that folks are also interested in the radio amateur world, where some of the transequatorial propagation.
Yeah, it has to be at right angles, and Japan sort of is straight. Southern Japan
cuts straight through Japan. Oh no, there's Japan up there. Sorry.
Yeah. Well, see, Japan is at right angles to this.
Yep.
And that finishes up sort of outback Queensland. You need to be, and there's been 2 metre contacts between Japan and Queensland.
Right.
Fair while ago, probably. That thing I think could be far more frequently with digital modes.
Yeah, that's right.
Okay.
Right. Now, the thing that interested me here was there were 6 metre decodes without anything on 2 metres, and I started looking at the individual decodes because I thought, well, maybe they're meteors, and some of them would be, but on the next slide you'll see that earlier, sort of 1500, 2 metres was in, and clearly this is spread like auroral propagation, and then it's later at 1700, 2 metres is in again, and this period when 6 metres was decoding is here. There's a noticeable drop in signal strength, sort of minus 9s and 10s, and 10s and 11s here, and 17s and 15s. But then they're obviously not meteors, because if they were meteors you'd see strong little bursts of a second or so.
Yeah.
So there's some sort of they're spread like the auroral propagation. They're decoding on 6 metres and not a sign of them on 2 metres. And I guess Andrew and I are guessing that there is some weak ionisation, weak residual ionisation and 6 metres is still able to use it.
Yep.
But not
But it drops out for 2.
But not for 2.
Okay.
Uh,
Okay.
Alright, next slide.
More intrigue.
Now,
The Eye of Sauron.
Yes.
the forecast on the 2nd of December was that there should be a nice Kp index increase up to 5.67, and this was related to a big hole in the sun's atmosphere, which people suggested should produce a whole lot of energy leaking out towards us, and it's sort of straight on to us at the Earth.
That's a pretty massive hole.
It is.
It is.
In the scheme of things. Like, how many Earths can you fit across here?
Yeah.
So yeah, some
So,
million
so we're
kilometres across
expecting big stuff, but neither Brodie or Jeff, I ran it the whole night, I transmitted the whole night, neither Brodie or Jeff saw anything. Well, Brodie saw absolutely nothing. Jeff had a few decodes, which we will talk about in a minute.
Okay.
So next slide. This is Jeff's decodes, and you can tell these are meteors. You see the little burst
Really
here and a
short.
burst
Yeah.
here and a
Yep.
burst here. And there's actually a weak little burst here.
Yeah.
It's amazing how WSJ or Q65 only needs a burst of a few seconds and can still decode.
That's pretty amazing.
The other clue that it's not aurora is it's all on 700 hertz,
Yeah,
is
there's
what
no
we're
shift.
transmitting.
Yeah.
So,
Okay.
That's
okay,
with some a priori information.
that's
from the
right.
decodes.
Yes,
That's
yes, that's right. It already knows both call signs. So.
Yep.
Now this is what the Kp and what we've found is called the Hp30 index is. And the
Hewlett Packard 30?
Yeah,
No?
well, it's the German people who produced this,
Okay.
and because it's only 30 minutes compared to the Kp index, which is 3 hours, there's a fair chance that the Kp index is sort of averaged.
Yeah. Okay.
And that it should show.
So there's
drop.
finer granularity.
Yeah.
That's
Now,
right. Yeah, so the Kp is planetary index, which is derived from a number of magnetometer sites around the globe. There's an Australian version derived from the network that the Bureau of Meteorology has.
yeah.
The HP index here is it's a measure. It's again a magnetically derived measure. It's a measure of the plasma effect in the ionosphere.
Okay.
That's quite well related to the Kp, but as Rick said, it's got finer resolution, so can be kind of more useful.
But even so, the HP index only rose to 3.6, so the forecast of 5.6 was well out.
Okay.
And in the Australian region, it only got to 3.
Yeah. Okay.
So it's not surprising that nothing happened.
Is there a correlation between the value, so the quantum of the Kp and the volume quantum of the HP30?
Yes, there's a fairly good correlation,
Okay.
but more resolution.
Yeah, so these are quasi-logarithmic scales. You
Okay.
know, not quite as logarithmic as say the Richter scale, but it gives you some idea that big numbers are good for auroral stuff. I think the HP index from memory is from the horizontal magnetic field component, which is the one I've been shown. So,
Okay.
I mean, we can even derive probably a local version of that from a Hobart magnetometer.
Okay. Well, we might have a better measure.
But on that case there, as Rich will say, the solar wind from that hole was kind of more constant in speed and not as fluctuating, whereas the previous event, 1st of December, was from a coronal mass ejection from a flare that was pointing in the direction of Earth, and we got what's called a halo coronal mass ejection.
Okay.
Basically, the solar disk was covered in this ejected plasma as seen by the spacecraft, and then eventually reached us. But also blowing along behind some other coronal mass ejections, compressing them and speeding up and causing more fluctuations, more energy in the system.
Okay. More variations. Yep. Okay.
Now the 40 or 45-minute forecast also shows that this was the closest it got to Tasmania was a fair way away, so it wasn't. We wouldn't expect on that basis to see it, but the reality is you get a bit of an idea from their 3-day forecast that it's worth having a go. And I just transmit all night, and Brodie and Jeff receive all night, and if it happens to work, it works. But
it's good that you have a system where you can do that.
yes, well, WSJT helps a lot.
Correct.
Correct. Now, what I've done here, I've gone back and found my record keeping's not perfect, but I think I have found all of the auroral events that we've had, and plotted them all on top of each other. With different colours for different events. It is pretty clear that before magnetic midnight it is generally positive, and after it is negative. You would, on the basis of this data, and there's really only two events, the blue and the green, are slightly skewed before magnetic midnight. So I think we need a lot more data to.
That's showing the right sort of thing, and some of that variability will just be individual auroral type. Variability in those cells aren't necessarily perfect cells, so yes.
But consistent
Well,
shift.
that's right. Yes, there's a few things that are odd. A lot of these dots here are meteors right on zero shift.
Yep.
Or very close to zero. And for some reason or other, there's a series here that's 100 hertz off, and I don't know what caused that.
100 hertz is suspicious, Rex.
Yes.
That's.
I mean, it would be suspicious if there was another signal, stronger signal at the same time.
Yes. Yeah.
That you might have 100 hertz sidebands, but
correct.
there's no evidence of anything else. So
okay.
it was only on one, obviously the majority of that event, it was just there. We haven't got an explanation.
The other interesting thing is, there's kind of a maximum and a minimum Doppler shift, and I guess we're seeing some sort of median or weighted average, in those measurements. There may well be much larger Doppler shifts in individual parts of the beam, but I guess the beam averages things out. It'd be interesting to look at this with, smaller or bigger beams as well, to see if the averaging effect. I don't know. That's all.
Because that's part of what you're getting with between the 6 metre and the 2 metre difference.
There's some of that too.
That was because your 6 metre beam has a much more.
That's right. That's certainly
You're looking
true.
at more of the sky.
Yes, I'm just in my mind questioning whether it's possible to do averaging the way WSJT works. I think it just finds the peak.
So it takes the highest value, or does it?
Yes, it finds the highest, the frequency at which the sync is strongest.
Yeah. And
it plots. Then it looks for the message to the right of that. So I don't think there'd be an averaging.
No. It's more maybe
It's a joke question.
Yeah, that's right. The antenna pattern. The antenna patterns.
Yes.
But yeah, other things to think about.
Yeah.
But that's
That's nice.
that's consistent. That's like
Yeah, when Andrew suggested I should do this, I thought, this is going to be very painful, but it wasn't so bad.
I wasn't trying to inflict pain on it.
okay. Data manipulation.
Well, it was about finding the file.
Oh, okay, right. Data storage issues.
But having now got a set of files together, I can add to it.
Cool.
No, I know that it's worth adding
Oh,
to.
you'll be uploading it to Google Drive soon, Rex, and be sharing it with the world.
So that is
Cool.
it.
Cool.
Okay.
So if we go back to somewhere around here, let me go back to there. That's better.
Can we get any questions on that?
Yes, that was. Unfortunately, we're using the same machine as I am here. Just let me go to now. Okay, what we have is hello to Sean, Lionel, Paul, Ken, and Andy. Have we got any questions, guys?
Now Brody will be listening.
Oh, okay, cool.
He can ring me with a question. He hasn't worked
Ah,
out how
okay.
to be in the chat thing.
Ah,
yet.
cool. Okay. Now somebody did call me. I don't know whether that might have been 46 minutes ago. So yeah, about when we started. So it may have been an 03 number 44334. No, no. I don't think I've got Brody's number. But yeah, any questions from our audience? We've got nine watching at the moment. So
Cancel. Sorry.
go to information. There we go.
So it's 0488.
Oh, no, that's not it. No, it wasn't that person.
Okay.
Okay. So yeah, but what do you recommend for a headache? Oh, okay. Okay, yes.
Don't look at those convection maps.
Yeah, I agree with that. There's an awful lot of information on those maps.
I guess the other thing to mention is that solar activity is still fairly good at the moment. It get a bit of a lull, but we're now heading towards the solstice, and generally the auroral activity is not as favourable around that time. It's the equinoxes that are the best times. So,
Okay.
but there's always a good chance of seeing some stuff.
Well, true.
And in fact, the solar activity hasn't yet reached its peak, has
No,
it?
that's right.
So
So next
probably
year.
next year, around April,
Yeah.
might get some really good stuff.
Fantastic. I look forward to it. And yeah, the summer field day as well is coming up, so I hope for good conditions. No, well that is fantastic. Thank you, Andrew,
Yep,
and thank
thanks,
you, Rex,
Yep.
and thank you for putting that together. That I'll give you that back. Thank you, Rex. And I look forward to the
Why does
next
that get hot?
the next event. Yeah, no, it gets hot because it's a memory device. It's a piece of electronics. If it doesn't dissipate the heat, it's probably not working.
Right.
Someone's let the smoke out. So we hope for another one of these events, or even better
At the right time of night.
at the right, well and truly. So that's I happen when I have a look at this every couple of days. So if I happen to get to it at the right time, I capture it.
Right.
Because it just keeps going. So yeah, it's and I thought that's when I usually email you and go,
Is there anything to say?
is there anything to say? So
Well, spaceweather.com is a good source for stuff, and we use that quite a bit.
and in fact we'll we'll wrap up at that stage. I'll hold over the other bits and pieces. One of the things I thought that I would add at the end of these sessions is actually, and talking about, you reminded me, the Australian Space Weather Forecasting Service, which is actually run by the Bureau of Meteorology.
Yes.
It's an arm of the Bureau. Put out a fantastic couple of websites around space weather, and there's a wonderful dashboard which I'll post the link to in the chat in the description. And
The NOAA one.
no.
No.
This is
The Bureau's one.
this is the Bureau's one.
And it's your tax dollars at work for those
Oh.
who are paying tax in Australia.
Well and truly. And so there is a dashboard that gives you, and look for the red bits because that's the warnings. And like the current warnings are, there is a HF communications warning, which is CME-induced geomagnetic storm activity expected to commence mid-7th of December, extend into the 8th of December, degraded HF conditions expected during this interval. Then there is a HF, an accompanying HF fade-out warning for that period, the 6th, the 7th and 8th. And then there is the geomagnetic warning, which you had on one of your diagrams. You were
Yes.
labelling up the magnitude of that
Yeah.
that geomagnetic field. And so the 7th and 8th, the 7th is a G0, the 8th is initially G1, then declining. So, and this is all publicly available, all on your, as you say, your tax dollars at work here, and for amateurs, you log. I keep hearing these comments. Oh, HF is dead. Well, you go to space weather and you work out why it's dead. When I was doing the
And what it means is it might be alive
well
on Auroral.
but on a different frequency, like maximum usable frequency. So.
Exactly right.
The reason I said about the delayer and the TEC, I used to watch the TEC predictions and forecasts when I was doing the 630 metre experiments. Because as soon as you had one of these events and it injected all of these electrons and energy into the atmosphere, 630 metres just went dead. And it was just the first place you'd go is to here, look at the TEC and go, oh yeah, okay. Probably not going to have this for a couple of days whilst it dissipates. And that energy has to go somewhere. Because I understand the TEC, the Bureau measures TEC around, like for the power companies and that have big networks and
Like
all of that sort of stuff.
TAS networks.
Yeah.
That's right.
So there is there's a valid industry need for this. It's not just an exercise. So yeah.
And actually, one interesting little thing on the 1st of December there, I've got I just measure my GPS position might be every second, something ridiculous like that.
Okay.
But really, you get a fix every few seconds. But you can actually see position errors due to the ionisation, and on that particular case, you might get 40-50 metres
Of variation.
Of variation, yeah.
Yeah. Okay.
So
okay.
I just log that, and then I compare against, say, the 0 UT value, plot the the northings and the eastings from the location. And you can see the nice correlation with the magnetic field variations, and it's just the ionisation delaying the signals and shifting them around a bit. So even something, if you've got a GPS that you can log.
Leave running and
Yep. Either on the device or by serial or something like that.
Yep.
It's good fun.
Physics at work.
That's right.
I love it. All right. Given we haven't got any questions, I'll call that quits. Thank you very much, guys. And I look forward to the next event.
Well, according to this, it might be in a couple of days.
Well, I'm not sure.
It's only going for G1 and G2.
No, I think we're a bit bored with the low numbers now.
Yeah, we want high
the
numbers.
The G3s. That's right.
We want up here, at
Yes.
the major severe storm level.
That's right.
Oh, fantastic! All right, we'll bid you farewell. Now we're DATVing for the holiday period, so we will be around on a Wednesday night. So please tune in. We'll see you next week. 73 from the studio. Cheers.